Welcome to a new episode on the Technomora channel. We really hope you will enjoy watching it and invite you to tell us what you think of it by leaving your reactions below the video. And now, please allow me to present your host, Technomora.
A Triac looks pretty much like this little device here. It looks, in fact, very much like a power transistor. And it is labeled, the three pins are generally labeled as A1, A2, and G, or gate. Alright? So, A1 and A2 probably stems from the fact that a triac is actually pretty much like two thyristors connected in parallel and in reverse. So one thyristor pointing, let's say, down and the other one up. Alright? So pin 1 is actually A1. Pin 2, or the middle pin, is labeled as A2, anode 2, in other words. And the third pin on the right is labeled with G for gate. Alright, so that's how a triac looks like. Triacs come in many shapes and forms. Alright, and here I'm showing you a few of the different forms triacs can be bought in. So you have, for example, here you have a triac, a tiny little triac in a housing, a TO92 housing, so pretty much like a tiny transistor. Obviously, this one can only take a few milliamps, I think it's maximally rated for 100 milliamps, that one is. And then you have the more common form, which is this TO, I think this is a TO7 housing, pretty much like a power transistor, alright. So, and this one is rated, if I'm not mistaken, for 10 amps, yeah. And then you have the power triacs like this one here. And this one, if I'm not mistaken, is rated for 20 amps. Alright. Alright, now the Triac is designed to control AC current. Alright, and this is represented on this little diagram by the sine wave here. Okay. So now you can divide this sine wave in 4 quadrants, basically. So you have a quadrant 1, 2, 3, and 4. Now, the triac, by of preference, conducts either in quadrant 1, which is the first half of the positive sine wave, alright, or in quadrant 3, which is the first half of the negative side of the sine wave. Alright. That is, if the A1 and A2 pins, or let's say the A1 pin of the triac is connected to the AC, and its gate is connected to the same AC. Alright? So in other words, the current that flows to the gate of the triac follows the AC that runs through pin A1 and ultimately, of course, through pin A2 of the triac. So if the gate and the current the triac controls flow both simultaneously through the triac, yeah, the triac will conduct in this first half of the positive sine wave. Alright, so in fact it will stay conducting a little bit beyond that until the current that flows to the gate, yeah, drops to below the holding current. If the current that flows through the gate is less than, or I'd say 20 or 30 milliamps, the triac will stop conducting and the voltage at its pins will suddenly, or I would say the voltage coming out of pin A2 rather, will suddenly drop to 0. Alright? And it will stay 0 until the voltage starts to run negative on pin A1 and the gate, and then it will start conducting again. And it will keep conducting until the current that flows through the gate again drops somewhere below, let's say, 30 milliamps, and then it will abruptly drop back to 0 again. So in effect, you get an incomplete sine wave that flows through the triac. Now it's illustrated in a different way with this little graphic I'm going to show you. Now remember I told you that the triac will let pass current through its anode 1 and then out in its anode 1 and out its anode 2, as long as its gate is triggered with sufficient current. Alright? Now, remember, the triac is a device meant to control AC voltage. Although you can control the triac with either positive or negative DC voltages on its gate, obviously it will preferably be controlled by AC voltage on its gate, and if possible AC voltage which is let's say coupled to the AC voltage, yeah, that the triac or the AC current the triac will try to control. Alright, so if you set AC voltage on the gate of the triac, which runs, let's say, in parallel with the AC voltage to be controlled, you get a graphic pretty much like this here. Alright, so what you see here is basically so what I showed you in the other graphic, which is quadrant 1, 2, 3, and 4. And in quadrant 1, which is the first half of the positive sine wave of the AC current, if you put a similar AC current on the gate, you will see that the triac will start to conduct at a certain voltage and current level, yeah, and then depending on the voltage and the current you put on the gate of the triac, it will start to let through more and more current, AC current that is, through its A2 output. Yeah? If A1 is the input, A2 of the triac is the output. And it's the same thing in quadrant 3, but then for the negative first half of the sine wave of the current. Yeah. So if the gate follows exactly the to be controlled AC current, it will conduct first slightly and then suddenly, abruptly, at a certain current limit, which is a few milliamps, yeah, the Triac will suddenly conduct and then will let through more or less proportionally to the amount of current on its gate, will let through a whole amount of AC current, okay, through its A2 output. Now, this is depicted here as if the gate is controlled by, let's say, AC voltage, which follows the to be controlled AC current. Yeah. Obviously, you can control a Triac with DC voltage on its gate, but depending on the polarity of the DC voltage on the gate of the Triac will either conduct as depicted here in quadrant 1, yeah, or if the polarity of the DC control voltage is negative, in quadrant 3 here, yeah. And to be more specific, that would be mode 3 negative, and here that would be mode 1 plus. Alright, so this little one or this little one here. Okay. Now, obviously, controlling a Triac with DC, although that is possible, and it will work, it won't be as efficient, of course, as when you control the Triac with AC current on its gate. It's January 2022. I want to reassure you that there was nothing really bad going on, and yes, I was silent for a reasonably long while, but I had to get through a particularly bad bout of pneumonia combined with a flu and general exhaustion. But now I'm back. I'm back here. I got through it without let's say too much trouble. It just took me a while to get back, on top of it. And yeah. Also, I didn't want to jinx the new year by wishing, everybody a new year. You know, the times being what they are, very, let's say, unpredictable. I prefer to make it a fresh start and start the new year with a whole bunch of new projects. And let me tell you, there's so much stuff that I yet have to do and finish. There will be plenty of videos for 2022 to make. Either way, I decided that the best thing to do to start afresh in the new year is to finish a project that I started last year, which is building a homemade multifunctional power supply. So let's get into it. Like I said in the introduction, I wanted to build a simple high voltage power supply module. And I built it around a Triac, alright? And you can see the symbol right here for Triac. Now, basically, what we're going to do is we're going to use a Triac to to control an input AC voltage and to either lower or increase that AC voltage that goes to what is better known as a Cockcroft voltage multiplier. Some people also call it a multiplier, a voltage multiplier ladder, yeah, diode ladder, you could say. And in this case, we're going to build a quintupler, which basically means something which multiplies a certain AC voltage to a DC voltage, which is 5 times higher than its input AC voltage. To be more correct, 5 times higher than about half the AC voltage you put in to the circuitry. Okay. Now, each diode you see on this diagram is a multiplying step, right? So that means that AC voltage which comes in diode is being rectified and used to charge up the capacitor following the diode, right? And that goes all through this circuitry here. So every diode produces DC voltage which charges up the capacitor connected to it. And there are 5 diodes, so there is a theoretical multiplication by 5 of the input AC voltage. Now, the Triac you see here, we will control with a little circuit, see here, right, at its gate. And that Triac will control AC voltage which comes out of this isolation transformer. And this is a true isolation transformer. So it is a 1-to-1 ratio transformer, meaning that voltages do not get lowered or increased through the transformer. They are just being separated from the AC voltage which comes from the AC outlet in your lab or in your house. Alright? So why do I do that? Well, simply out of safety measure. Yeah. It's a safety measure. It just makes sure that you can never ever be connected to the AC wall outlet, all right, which would be truly dangerous and absolutely lethal if you don't know what you're doing, that is. But either way, I thought it would be much, much safer to do that. And the isolation transformer is right there. It's not a very powerful transformer. It's about 5 watt output power. But this will be more than enough to power a high voltage either negative or positive DC power supply module. Now, to make it even safer, I decided that to control the Triac, I would not connect a potentiometer directly to it, which would well, theoretically at least, put my body close to live AC voltage. So instead, I'm using a little circuit which will control the Triac via a light dependent resistor, or LDR, the symbol right here. And the control circuit is really nothing more than a voltage stabilizer, in this case an LM317, which we will use via a potentiometer to um, send voltage to an LED, a white LED, and the LED's brightness will control current that flows through the light-dependent resistor, and thus we will control the gate voltage of the Triac. I did that simply because I really wanted to have a galvanic separation between the control circuitry and the human operator. All right. Obviously, we're going to feed this circuit with rectified DC voltage from the main power supply. All right. So there you go. That's in a nutshell is what we're going to build, and that is exactly what you see down there. Okay, so don't worry, I'll get you, or I'll give you all the values of the components later on in the video. Now, I'll give you a little demonstration of what the circuit does, and once we've done that, what I'm going to do next is transfer all that circuitry you see here, which I'll admit empirically tested out. We'll transfer all of that to a standard little PCB. In fact, the type of PCB I've been using to build each and every module of my homemade power supply. Alright, so what is the next step? Well, the next step obviously is that we're going to transfer the components on this breadboard here to a PCB, a standard size PCB. In fact, this is the size of PCB I've been using for every module in my power supply until now. It's a 5 by 7 centimeter double-sided perf board PCB. All right. These tend to be reasonable in quality, so I haven't had too much trouble using this particular brand of PCB. So the next video you see is when all the parts you see here on this breadboard here will have been transferred to this little PCB. And I have a good hope that once I've done that, the efficiency of the circuitry will go up a little bit. So meaning that the output DC power will go up a little bit. Alright? So let's lower the voltage now. There you go. So there is a bit of a lag, of course, because the capacitors which form the multiplication ladder need to slowly discharge their power to the output. Now mind you, this voltage here is without load. Alright? There's no load involved here. If there is a load attached to the output voltage will dramatically drop. Alright. So I calculated the output current to be no more than a few microamp. Okay. So you'll say, oh, microamp, really? Well, yes. I wasn't joking when I said I wanted to keep it safe. Alright? And basically, we're going to use it, this little power supply, to test vacuum tubes. Right? So, and vacuum tubes often work in the nanoamp to microamp range, right? Rarely in the microamp range. So yeah, there you go. So um, we'll have rarely in the milliamp range. All right. So we'll have, let's say, enough current and high enough voltage to test, let's say, most simple vacuum tube circuits. Alright, I'm going to build my own little opto controller, which consists of an LDR, so this component here, which is a light sensitive resistor, and a small 3 millimeter white LED. And it's not warm white, but very bright white. All right, I think that in Kelvins it's about 6,000 Kelvin color. Yeah. So I know some of you might wonder, why would I make my own optocoupler if you can buy them ready-made on the market? That's a good question. Um, Partially because out of curiosity, I would say, and also because I thought it would be fun to make an optocoupler myself, and just to see physics in action, you could say. So the optocoupler really will consist of these two components you see here, and of a piece of black, uh, non-transparent shrink tubing like this. Yeah, and we will fit the LED inside of it on one side, and we will fit the LDR, which is this little component, into the other side of the tubing. All right, and we will make, or rather I will make sure that the components meet somewhere in the center of the tubing, right? And the LDR, in fact, will rest right up, will butt up right against the LDR, somewhere in the middle of the tubing. All right, and then once that is done, I will shrink the tubing around the two components to keep them in place. Now, I'm still debating a little bit whether I should glue the LDR to the LED or not. I'm still debating with myself on that. Um, I think in the end maybe it wouldn't be a bad idea, because that way I can keep the components really straight and pointing towards each other. So in effect, what I'll do is I'll use a little bit of super glue, yeah, and I'll glue the two components straight up like this against each other, right? Uh, and then we'll mount them inside the tubing. Now, I'm not sure whether I should put the LDR into the tubing first, then put some glue on the LED and then push it inside the other end of the tubing, or whether I should do it now first before I build it, as it were, inside the tubing. I'm not sure. So yeah, give me a moment to think it through, and well, once I'm done, I'll show you the result. Now, to show you the resistance of the LDR, I connected it up to my multimeter and I obscured it. So right now the resistance of the LDR is 2.45 mega ohm. Alright, so mega ohm. But it's incredibly sensitive. So even the slightest bit of light makes it react. So right now my bench is illuminated by my bench light. Now watch what happens to the resistance of the LDR when I switch off my bench light. Alright, so here we go. You see, the resistance goes up to 2.56 mega ohm. Alright, so it's so incredibly sensitive that even through black shrink tubing and covered up as it is by a heavy roll of solder, it still registers a slight difference of light intensity. So yeah, there you go. I switched on back my bench light. Now it's 2.4 mega ohm. Okay, so the slightest change in brightness around the LDR makes its value change. Yeah. Now, watch what happens when I remove the roll of solder from the LDR. It's inside a piece of black shrink tubing, right? Now watch this. The resistance of the LDR dropped to 430 kilo ohm inside that little piece of black shrink tubing. So yeah, it's incredibly sensitive to light. And by the way, it reacts to white light, but it also reacts to warm white light and even to red light. Because when I illuminate the resistor with my laser pointer, it also reacts. So theoretically, I could use a red LED instead of a white one to control it. Now, the value of the LDR when it's completely illuminated is close to, well, nothing. Obviously, it's not nothing. I'll show you the value completely illuminated. Let me show you. Alright, so yeah. So right now it shows 0, but I'm on the highest scale on my multimeter, alright? So let's see if we put it to the 2 scale. Alright, so watch what happens to the resistance. I don't know if I can show you both in the same shot. Let's see. Okay, so alright, so watch what happens when I illuminate the LDR with my pocket light. So the resistance drops to, I'd say, close to 160 ohms. Yeah. Now watch what happens when I illuminate it with my laser pointer. See? So the LDR is extremely sensitive to light changes, which means that I will have to take great care mounting it inside the shrink tubing, and in effect I think I will even put two pieces of shrink tubing, one on top of the other, to darken it even more. Alright, in the end I ended up by uh, gluing the LDR and the LED inside a short piece of shrink tubing with some hot glue, and I used actually transparent hot glue because for the moment that's all I have. Alright, so this kind of hot glue, and I injected with my hot glue gun hot glue on either side of the tube. Alright, so but I inserted the component, the LDR first, then I injected hot glue behind it. I waited until the hot glue set, then I turned it around, placed the the LED inside the tubing, and then I injected some hot glue behind it, and I waited until that set, and it seems to have worked. Yeah. The the component that I made, so the optocontroller, is really rather rigid. Yeah. Now, to make sure that there is no light, well, at least no excess light coming or reaching the LDR inside of the tubing, what I'm going to do is I'm going to encapsulate the hole with another piece of black shrink tubing. Something which I'm going to do right now, in fact. So, let me show you. There you go. Alright, like that. Okay, perfect. Now I take my soldering iron. So let's see if I centered it correctly. Yeah, I think I did. Okay. So, about there. Yeah, about there. Right, let's go for it. Yeah, and you can see the um, shrink tubing squeezing some of the hot glue out of its end here. So, but you can simply retouch that with the soldering iron like this. Alright, so you can melt it locally, slightly, with the tip of your soldering iron like this, and work it up a little bit like that. Alright, there you go. It's not the neatest component, but it'll do what it must do. So Voila. Alright, so now we let that cool off. And that will be it. Alright, all the AC parts, so all the parts which are connected to the AC voltage, are located and soldered on the perf board. Next, I need to mount the diodes and the high voltage capacitors, including the high voltage electrolytic filter capacitor. Alright, so I just need to transfer these parts to there, and then let's say 90% of the board is ready. And thanks to the miracle of video editing, there it is, completely finished and tested. Now I feel obliged to repeat yet again that the power supply project is built out of several little print boards like this one here. You could say separate little modules. And the reason for that is very simple. I wanted to have a design which I can expand or improve on rather easily. So I kept several of the functions of my power supply design separate on little boards like these. Okay, and that way that allows me to later on at a later date replace a board, for example this one, by a new design rather easily. That's also why I'm using connectors for connecting potentiometers and power supplies to a little board rather than soldering the wires directly onto the board, which obviously would be simpler and a tiny little bit cheaper. But this sort of design allows me a lot more flexibility. So before I give a small demonstration, let me point out a few things quickly of the power supply, alright, the high voltage power supply. So right here you see a isolation transformer. Okay, so this is a 1-to-1 ratio transformer, so it will basically do nothing more than physically separate the AC voltage, which comes from the power outlet, to an identical voltage at the same frequency, which is in my country 50 hertz, yeah, to the other side, to the power supply board. Alright. The transformer is rated for 5 watts maximum, and this is more than enough to power the little power supply board. Alright. So obviously this transformer will be built into my power supply case, which I'll show you later on. And it will also power both high voltage boards. So this is the positive high voltage board. I need to build a negative DC output high voltage board, right? And that one will also be powered by the same transformer you see here, right? Okay, so what you see here, basically, let me see. So what you see here is basically a galvanically separated high voltage, uh, let's say, side of the power supply, and a low voltage control side of the um, power supply board. Now you might say, what do you mean by galvanically separated? Yeah, well, the low voltage control side, yeah, so in effect the electronic switch will control how much output power the board will give, is physically separated from the high voltage side by a homemade optocoupler. And the optocoupler is this little black tube you see here. Yes. Basically, it is an LDR, so a light dependent resistor, which sits opposite an LED. All right, and the LED is pointing at the LDR inside that little black shrink tube. Yeah? And the only advantage, if you could say it like that, of this is to make sure that the low voltage side, which is connected to a potentiometer here, yeah, is physically separated from the high voltage side. So in theory at least, I can never get a high voltage shock, yeah, because they are separated. By the way, that principle of separation is also done by the isolation transformer. All right, so the little transformer you see here, yeah, does in effect do more or less the same thing. You know, it separates um, the power supply from the main AC. So basically, how does it work? Well, there is a Triac here, yeah, which gets its power from the isolation transformer via a few components like a resistor and a capacitor, etc. Yeah. And as some of you may know, a Triac consists of two, um, well, of an input, an output, and a gate. All right. Um, Now, a Triac to conduct needs a minimum amount of current to do so, and the current to switch on the Triac is provided either in this direction uh, via the direct output of the isolation transformer through this main capacitor here, yeah. Or it is provided on the other side of the isolation transformer secondary winding via a load resistor you see here, which is a power resistor, by the way, and via this LDR, and I'm back here into a Diac. All right. Now the Diac, you could say, is a the equivalent of a DC Zener diode. All right. The Diac makes sure that the Triac can be switched on with just enough power, but never too much. All right. So the Diac will take care of that. All right. And the Diac is, in fact, you could say, a small Triac without the gate. All right. So just two thyristors which are mounted in opposition, basically. All right. So this is, you could say, a voltage and current limiter. Yeah, pretty much like what you would find in a DC circuit with a xenon diode. All right. Now the LDR makes sure that the LDR provides the means to either squeeze the amount of voltage and current going to the gate or to allow more of it. So in effect, to make the triac either conduct more or less. All right. Now, remember I told you that the control is done via a galvanically separated control mechanism or component, which I made myself, which is in fact um, a optocoupler. Yeah, so an LDR, a light dependent resistor, mounted in opposition to a white LED, like you see right here. All right. Um, you might say, okay, but why did you make one yourself? You can get those basically ready-made. Um, True, but I just wanted to test out whether I could, in fact, make one myself and how well it would work or not. And it works surprisingly well, actually. So, the distance between both inside the tube is really not very critical. In my design, there are a few millimeters space between these two components. Yeah, but the distance, like I said, I mean, if it's within a few millimeter, really doesn't really matter. All right. Now the brightness of the LED, which of course is important, because that will allow to set the resistance of the LDR, and therefore the amount of current that will flow through the circuit, the power circuit, to the diac and into the gate of the triac. Okay, so you need to have something to set the brightness of the LED, and that is really quite simply done via this little circuit which you see here. All right, so obviously, this part is connected to the DC output of the mains DC output of the power supply. Yeah, the main DC output, and then is let's say brought down via either in a first step via an optional resistor and xenon diode pair, or if not needed, then directly via the LM317 power regulator integrated circuit. So basically this brings down the incoming DC voltage to a stable 3.2 volts DC. All right, and the 3.2 volts DC itself will be admitted to the LED via a small transistor. And this transistor here is basically a small NPN transistor of the type, let's say, BC547. Yeah, it's nothing special. The amount of current you need for the LED is about 15 milliamps, and BC547 can handle that very well. And it's only very low voltage, by the way. It's about 3.2 volts DC. All right. Don't worry. I'll publish the schematic later on in the video. And you'll get ample time to look it over by pausing the video. Now, like I said, for the DC part, the the input resistor, which is also a power resistor, and the Zener diode, yeah, are optional. I mean by that if the incoming power is higher than, say, 35 volts DC positive, yeah, then you need to bring that down to a voltage at or below 35 volts DC. All right. You need to do that because the LM317 can't handle more voltage than 35 volts DC. All right. So there you go. In a nutshell, that's how this really works. Now, like I said, I'm not going to explain the working of a Cockcroft voltage multiplier ladder. Um, there are plenty of articles explaining the functioning of that, but I'll include a link down below the video to a website or websites where they explain exactly how a Cockcroft voltage multiplier works. Alright, a quick recapitulation of what you see right now. So over there is the power supply, which will deliver DC voltage to the power supply, the high voltage power supply board here. Okay, so in effect, that voltage over there will be used to control the brightness of the LED in the optocoupler. Alright, so now this here, this multimeter here, indicates the AC which exits the Triac and which goes into the voltage multiplier ladder. Alright, and then the other multimeter you see here indicates the DC output voltage of the power supply board. So in effect, the high voltage which exits the power supply board, and it's obviously positive. Okay, so plus DC volts. Alright, so the potentiometer, which controls the brightness of the LED, is right here. So now you see the potentiometer is at its lowest setting. So the minimum amount the Triac can output is not 0 volts, but is 35 volts. Alright, because when you take a good look at the schematic, you'll see that the diac always get fed some amount of current. Alright, so the Triac will always conduct, but at a very low level, you know, as long as the potentiometer is at its highest resistance setting. Alright, so which means that the output, the high voltage output right now, is around 75 volts DC positive. Alright, so the AC voltage, which is right now input into the Cockcroft multiplication ladder, yeah, is 35 volts AC. So you see there is basically, you could say, a doubling of voltage going on. A little bit more maybe, but not much more. Again, if you wonder why, since this is a quintupler, yeah, not just a simple doubler, but a quintupler, you might wonder, okay, how come that the voltage is being doubled basically and not multiplied times 5, you could say. Well, that is because this setup here is not really very efficient. There are all sorts of resistances and capacitances which influence the efficiency, the overall efficiency of the Cockcroft multiplication ladder. Yeah. So unfortunately, that's how it is. Now, in a later stage, I might design a new type of voltage multiplier, and that might be a lot more efficient than this one. All right, so don't forget, this is really experimental. All right. All right, so it's certainly not meant as a commercial design. It's purely experimental and for my own needs. Um, but if you follow along, obviously, well, you will build it for yourself too then. Okay, so now let's change the setting on the potentiometer. So here we go. So let's go to maximum first. Alright, so now the potentiometer is at maximum. You see the high voltage, the output high voltage is 227 volts DC, or 226, thereabouts. Yeah? The AC voltage, which is exiting, you could say, the Triac, is right now 158 volts AC. All right. Now, again, you might say, but how come that the voltages are so low, basically? Yeah. How come that you input 158 volts AC into the multiplication ladder and you only get out 226, which is not even double this voltage? Well, again, this has to do with the efficiency losses within the circuit. All right. The higher the voltage is that goes through the Triac, basically, yeah, the more critical the frequency becomes, and the current, the amount of current you put onto the gate of the Triac to control the voltage. Yeah, and the circuit is not very efficient at its highest setting. So, or you could say at the highest gate current that I'm putting into it. Okay, so again, this could be changed. This could be optimized, I suppose. But I simply ran out of time for this project. So for now, this will have to do. What you will notice, however, is that the lower the DC output voltage is, yeah, of the multiplier, the higher the multiplication factor will be. Yeah, so lower input AC voltage will create, relatively speaking, higher output DC voltage. So if I diminish it, and I'm turning the potentiometer right now, you'll see at a certain stage the voltages diminish. Yeah? And that has to do with, of course, the brightness of the LED getting less and less and less. Okay, here we go. Come on. Yeah, there you go. So now, voltages are lowered. Oh, yeah, it's quite sudden. So it's a very subtle setting. Let's see, there you go. So now we are inputting 55 volts AC. We are outputting 110 volts DC. Alright. So in effect, right now we get a doubling of the voltage. Yeah. So Yes, the circuit could be perfected, it could be improved upon efficiency-wise, but that will be a job for another day, you know, when I feel like working on my power supply again and designing a new module. Either way, I'm reasonably happy with how this turned out. It's simple, it's cheap, it does more or less what it needs to do. So giving me a stable high voltage. And by high voltage I mean basically a little below 100 volts DC to close to 200 or even a bit more volts DC. Yeah, which is more than sufficient to test, say, vacuum tubes and stuff like that. All right, so there you go. Um, Obviously, I'm not going to show you how I build the negative high voltage DC power board because, like I said, it's basically the same thing except for a few details. But what I will do is once all the modules of the power supply are built, I will show you uh, obviously all the modules that I built as I build them into the case of the power supply.